Hello all. This is a last minute addition to my channel, meaning that I'm recording this on a Saturday evening and it's paper 2 for the GCSE level from England. Okay, so this is the Edexcel curriculum, not the International Edexcel that I prepared some videos of in the past. So the channel started with international A level past papers and some lessons. Then I tried to expand into AS level, and lately I also uploaded a few GCSE papers. And from what I saw, people finds them extremely useful. But I focused on international tests. So today I'm gonna do the UK one, okay? And I believe the test is taken on Monday, so I don't have a lot of time in my hands to do this. So I'll do my best. Hopefully, I will finish it and upload it. Okay, so there are two tiers, by the way. This is the higher tier. I don't know what that means. I'm assuming it's harder. I don't know. And there is also the lower tier. I decided to go with the higher tier. This paper 2 from 2024. It was the only one I was able to find online. I mean, I'm pretty sure there must be the 2025 one out, but I couldn't find it. So we're going to go with this one. Okay. Since this is a video watched by first time viewers, probably, okay, I always tell my students that they should devote about a minute per mark, which means that this paper lasts for an hour and 45 minutes. That's 105 minutes, right? And it awards about 100 marks. By the way, I don't know why that pops up in the bottom every time. Let me switch it off. So the paper awards 100 marks and you have 105 minutes. So if a question awards 10 marks, it should take you about 10 minutes. This is to time yourself so you stay on time. So that's a very general thing to say, okay? Another thing I tell my students is, in the International GCSE paper, the formula sheet is in the beginning of the paper. So let me try to go to the back. Another thing I tell my students is to read all the formulas they give you. I mean, whenever you don't know how to work on a problem, just go to the formulas and just inspect them. Maybe you will get the inspiration needed to start the problem, okay? Another thing that is kind of obvious, but it's good to keep in the back of your minds. I once read that in France, at some point, students had trouble with mathematics. So to help the students, the French government decided to give them more language lessons, okay? Because the problem was that they couldn't understand what they were reading, okay? So read problems thoroughly, make sure you understand what they are asking, read again if it doesn't make sense, and then respond. So that's the other thing. And what else? Sometimes you might read a problem. So for example, here we have problem 1. Maybe part A doesn't make sense, okay? But then maybe you go to part B and you know how to answer part B, and then part B helps you answer part A, and part C helps you with maybe, I don't know, part A, and so on and so forth. So it's important to read the whole problem before you attempt the problem, okay? If that makes sense. What else? I think it's time to start, okay? I've said enough, probably. I had something else in the back of my mind and I forgot. Oh, and the other obvious thing, if you cannot immediately start on a problem, so if you start here with problem 1 and you spend more than 3 minutes and you still don't know what to do, skip it, okay? It's better to build momentum by solving problems that you know how to deal with rather than wasting time without going anywhere, and then that's going to have a very bad effect on your psychology. You will feel like, oh, I don't know this, and then that's going to drag to the other problems, etc. So go over the problems you know how to solve first. So anyway, enough said, let's start. Question 1. This question is about static electricity and electric fields. Question A. Figure 1 shows 3 charged objects x, y, and z, and y is positive, as we can see. Y has a positive charge, and is held stationary. The charge on y causes X and Z to move in the directions of the arrows. Which row of the table is correct for the charges on X and Y? So before we see the table, okay, so X is going to be negative, right, because it's attracted to Y, and Z is going to be positive because it's repelled, right? So which row is that? Charge on X negative, so it's either A or B, and we need positive charge on Z, so the correct answer is B. Okay, so that's a good start for us, I guess. Okay, so moving on to part B, give the meaning of the term electric field. So an electric field, and for those of you who are first-time viewers, my handwriting is horrible, and I do my best to improve it, but you can only do as much, I guess. I mean, I'm an older guy, so but okay, this is not an excuse because I had a horrible handwriting from the first day of elementary school. It was my mother calls it chicken scratches. So I'm gonna do my best, guys. So an electric field, okay, oops, is a region in space. Okay, is a region in space in which a charged object experiences a force. In which a charged object experiences a force. Okay, and for the record, I only taught AS and A-level physics for a year, but I also taught university level physics and even graduate level physics. Okay, so I'm trying to say I never taught at the GCSE level. I don't know what they teach you, but they should probably tell you this, that electric fields exist everywhere in space where charged objects exist. Okay, so it's a concept that helps us understand how electric forces work. Okay, so I think this is good. Oh, and in questions where you need to write the answer, I mean, like sentences, I try to read as I write, if that makes sense. So anyway, let's move on. Part C. Figure 2 shows the electric field around a point charge. Okay, and we see some distance x denoted there, and the point charge points out, which means that that's a positive charge. So let's see what they are asking. And I haven't seen the paper. I mean, I'm solving it as we speak. Okay, so that's the other thing. State how figure 2 gives evidence that the point charge is positive. Okay, the lines point outward, I guess, right? So all the field lines point outward. Okay, is there anything else we need to write? So you can write in parentheses that field lines point away from positive charge and into negative. Okay. So the idea is that if I put a test charge, a positive test charge, where the red dot is, it's going to experience an outward force like that. Okay. And if I put a negative charge, which I denote with blue, I don't know, it should be the other way around, but anyway, so if this is negative, it's going to be pulled in. Okay. All right. That's good. Let's continue. Question 2. In figure 2, x is the distance from the point charge. Okay. State how figure 2 gives evidence that the electric field strength decreases as x increases. Okay, let me think about that. So the spacing between field lines Okay. Tell us about field strength. Okay. So widely spaced lines mean a weak field. Okay. And closely spaced lines mean a strong field. Okay, maybe this is a little bit of an overkill, but okay. But anyway, so that's the essence. So if we look at the scheme, as x increases, so for example here, if we take x over there, you see that the lines are kind of closely packed. But if I move there, the lines are more further away. And if I am out here, okay, if I continue these lines, okay, so if x was down there, then look how far apart the lines are. Okay, so that tells you that the field decreases in strength as we move away from the point charge. Okay, so let's write that down. As x increases in figure 2, okay, the lines spread further apart. So this means, which means the field gets weaker. Okay. Okay, this is a 1 mark question, so maybe I wrote a little bit too much, but okay, this is supposed to be a lesson, so I'm trying to explain things as better as possible. Okay, so let's move on. Okay, there is a part 3 to this. So, okay, figure 3 shows a graph of electric field strength against distance x. The equation relating electric field strength to distance x is electric field strength is equal to A over x squared. Okay, A is a constant. Using data from the from the graph in figure 3, calculate the value of A when x is 3. Okay, I'm gonna need to bring my calculator next to me because I will need it. Okay, so x is 3 centimeters is this point over there. Okay, so the value, okay, if we take this point at 3 centimeters, we see that the electric field strength is 20,000 newtons per coulomb. So if we write E is A over x squared, then A, the thing that we want to calculate, is x squared times E. Okay, so in the answer we see that they use centimeters squared. Okay, so we are going to use 3 squared and then centimeters squared. The way I work, I try to arrive at the final algebraic expression. Okay, so like this one in the red box. Okay, and then I plug in the numbers and I put all the numbers to the left. So numbers go to the left and units go to the right. Okay, so units are over there. Okay, so 3 squared times 20,000. So that's 9 times 20,000. So that's 180,000, right? So 180,000. I'm going to erase this circle and I'm going to also write it here. So 180,000 newtons times squared centimeters over C. Okay, that looks okay. So this was question 1, guys. So question 1 down. Let's move on to question number 2. Okay, question 2, figure 4 is a circuit diagram. Okay, the current at P is, so we see that the battery, okay, so the battery provides a current of 0.1 amps, which then splits into this parallel section, right? So we get 0.05 amps in each branch, okay? And then these two currents merge again, right? So they merge again. So we need 0.05 amps plus 0.05 amps will be the current at P pretty much. So 0.1 amps. So B is the correct answer. I hope this makes sense. I mean, whatever you get out, you should get in pretty much. Okay, so it's kind of an easier problem than it looks. I mean, I don't know if it looks hard, but it's not hard. I think. No, I promised myself I'm not gonna use the word "it's not hard" in physics because it can always get complicated. So anyway, let's move on. B. Some students investigate resistors in parallel. The students set up a circuit containing four identical resistors. The circuit used is shown in figure 5. Okay. 4, yes, okay. The students measure the current from the power supply and the voltage PD across the resistors. On figure 5, draw a voltmeter connected to measure the voltage PD across the resistors. Okay, so that's the question. I guess, right? So we have to draw the voltmeter. So I guess here will work. Okay. So okay, that's good. The students remove one resistor and measure the current and voltage again with only 3 resistors in the circuit. They repeat the measurements of current and voltage with only 2 resistors in the circuit and then with only 1 resistor in the circuit. Figure 6 is a table of their results. Okay. Using data from the table in figure 6, predict the current from the power supply when there are 4 resistors in the circuit. Okay, so this missing value pretty much. Okay, so if you look at the table, we have 9.1 milliamps, excuse me, for one resistor. So that doubles to 18.2 milliamps for 2 resistors, 27.3 milliamps for 3 resistors. So therefore, we need 4 times 9.1. So the value will be 36.4, right? Yes. So let's write that down, 36.4 milliamps. Okay. Using data from the table in figure 6, calculate the resistance of only one resistor. So we can use this value, right? For one resistor, it's going to be the easiest. So this one. So we need the resistance. So voltage is current times resistance, right? So the resistance is voltage over current. What was the voltage? 6 over 9.1. So 6 volts over 9.1 times 10 to the negative 3. Don't forget to convert. So volts per ampere, which makes ohms, right? So let me do the division really quick. So the answer is 659.3 ohms. So 659.3, or maybe you can round it to 660 ohms. That would be fine, I guess. So let's move on to question number 4. This is a question in which you have to write down the answer, I mean in sentences, and it provides 3 marks. So the rule of thumb is to provide 1 sentence per mark. So here we have 3 marks, so we need about 3 sentences to describe or to explain whatever it is to be explained in the question. Okay, question 4. Using data from the table in figure 6, explain what happens to the total resistance of the circuit as the number of resistors in parallel decreases. The number of resistors in parallel decreases. Okay, so from the table, as we saw earlier, so from the table, okay, as resistors are removed, okay, the current falls. Okay, so you can see it here. So basically we have the lowest current for one resistor and the highest for 4. Okay, so the current falls. Okay, the voltage stays fixed because they are in parallel, so the voltage stays fixed. Okay, since V is I times R, okay, a smaller I must mean a larger R. Okay, so total resistance increases excuse me, as the number of parallel resistors decreases. Okay, so as the number of resistors in parallel decreases. Okay. So yeah, this is a complete answer, I think. So, I mean, physically, if you think about it, removing a parallel branch reduces the number of paths available for current, making it harder for charge to flow around the circuit. Okay, so the more branches, the better. I mean, for a higher current. Okay, so this was question 2. Let's move on to the next question. Okay, question 3. From what I see, this is about heat, probably. Okay, so let's read it. Question 3. A coil of copper wire has a mass of 14.1 grams. The density, rho, of copper is 8.96 grams per cubic centimeter. Calculate the volume of the copper wire using the equation rho is m mass per volume. Density is mass per volume. Okay. So we need the volume. So we're going to take this equation and solve for V. So V is mass per density, right? And you guys know how to cross multiply. I mean, this can be considered as rho over 1. So you have mass times 1 is equal to rho times V. And then the next step is that volume is mass per density. Okay. So they need the result in cubic centimeters. So, and we are given the mass in grams and the density in grams per cubic centimeter. So we're going to write this as 14.1 grams over 8.96 grams per cubic centimeter. Okay, so the volume is, let me do calculation really quick. So 1.57 cubic centimeters. Okay, moving on. B. Figure 7 gives information about the density of aluminium. So solid aluminium is denser than liquid aluminium, which is the case for most solids and liquids except water. Okay. Explain the difference between the density of solid aluminium and the density of liquid aluminium in terms of the arrangement of particles. Okay, so this is solid state physics, by the way. I mean, for those of you who will go on to study physics at some point in their lives, do I recommend that? I don't know. I'm gonna make a different video about that. So in the solid state, let's write the answer. So in the solid state, okay, particles are held in a closely packed A regular arrangement. Okay, so there are more particles per unit volume. Okay, I'm gonna need an extra space, so let's do that. When aluminium melts, okay, the particles gain energy. Okay, and move slightly further apart on average. Okay, so the same mass now occupies a larger volume. Okay, giving a lower density. In the liquid state. Okay, I think that's enough, more than enough, probably. Okay, so again, I mean, I don't know what they teach you in school, but in solid state physics, you learn that materials have usually some sort of a cubic structure. Okay, so these will be your aluminum atoms forming some sort of a crystallic shape, like a cube. Okay, and in solids, atoms are closely packed. Okay, so that's the answer. Okay, C. A student boils some water. Calculate the amount of thermal energy needed to change 60 grams of water to steam at its boiling point. The specific latent heat of vaporization, of water L is 2.26 times 10 to the 6 joules per kilogram. Use the equation Q equals mass times latent heat. So they should have told us here, I guess, that the water is at 100 degrees Celsius. Okay, so I mean, it is assumed, I guess. I don't know. Yeah, let's work with that. So Q is mass times the latent heat, and we need to provide the answer in joules, and we are given the latent heat in joules per kilogram. Therefore, we need to convert the grams to kilograms. Okay, so 60 grams, let me write it there. So 60 grams is 0.06 kilograms. Okay, so Q is 0.06 kilograms times 2.26 times 10 to the 4 joules per kilogram. So kilograms cancel. And we are left with, let me do the calculation, 0.06 times 2.26 times 10 to the 4. Something's wrong. 10 to the 6. I'm sorry. Yeah, I knew something was wrong. Okay. So the answer is 135,600 joules. Okay, moving on. D. Some students measure the volume of a lump of modeling clay using a measuring jug as shown in figure 8. Okay, using figure 8, estimate the volume of the modeling clay in cubic centimeters. You may assume that 1 liter is 1,000 cubic centimeters. So they give us the level of water without clay and the level of water with clay. Okay, so the subtraction will give you the volume of the clay, because we will have displaced liquid and so on. So do we need to justify that? Maybe you should write a sentence like the volume of clay, okay, equals the rise in water level in the jug. Okay. Okay, so let's see. It's a little bit hard to judge. So every deviation there is 100. So I guess 100, 200, 300, 400. Okay. So we have 1,350, something like that, without the clay. And with the clay, so I'm talking about that there. So to me, it looks like 1,350. And the other one looks like 16, 17. So that one is something like that. Okay, so let's subtract. So rise is equal to 1750 minus 1350, which yields 400 milliliters. Okay, and we need to convert to cubic centimeters. So 1 liter is 1000 cubic centimeters. So 1 milliliter is going to be 1 cubic centimeters. How do I know that? You divide by 1000 pretty much. Okay, so we have 10 to the minus 3 liters, which is 1 milliliter. Okay, so the volume is, in other words, 400 cubic centimeters. Okay, this was question 3. Let's move on. Question 4. This looks like an IQ test at the first glance. You know, the ones with the shapes that rotate and do stuff that they have in those tests. So, figure 9 shows an object at the bottom of a beaker of water. Okay, which diagram shows the direction of the force exerted by the water on the object at point X? Okay, I need to think about this. It's gonna be perpendicular, right? So that's the force. Okay, because the force, I mean, you have pressure pretty much on that side. I mean, you have to imagine that in 3D, okay? So the pressure is gonna push it downwards, and the pressure is force per area, okay? So B will be the correct answer, right? I mean, if you examine the other ones, so for example, C is totally wrong because it shows a force that points outwards. X is also totally wrong. And then, sorry, D is also totally wrong because it points outwards. So only A and B make sense, but it should be normal to the surface, okay? And acting towards the surface. So let's move on. Okay. Okay, question B. Figure 10 shows an ice skater skating on one skate. Calculate the force the skate exerts on the ice. And we have the pressure of skate on ice as 4.8 times 10 to the 7 pascals. The area of blade in contact with ice is 1.2 times 10 to the minus 5 square meters. Use the equation force is pressure times area. Give your answer to two significant figures. Okay, so force is 4.8 times 10 to the 7, and that's pascals, okay, times 1.2 times 10 to the negative 5, and then meters squared. So if we perform this calculation, we will find, I don't know if you can hear my calculator working. Okay, so 576. We need to remember that pascals is newtons per square meters. multiplied by the square meter, so that cancels. So we get 576 newtons. That's a lot of force. Okay, that's basically 55 kilograms of force. Okay. C. Figure 11 shows how atmospheric pressure changes with height above the sea level. Okay, above sea level, excuse me. So we, okay, so pressure reduces as we go up. Okay, that makes sense. Okay. Question I, using the graph, describe how atmospheric pressure changes with height above sea level is what I just said. So as height increases, um, as height increases, atmospheric pressure decreases. Okay. And also you can see that the relationship is non-linear. I mean, it's not a straight line like that. Okay. So it's some sort of a different relationship. Okay. So the relationship is non-linear. Okay. So pressure drops. Oops. More steeply. Okay. At lower altitudes. Okay. And more gradually at higher altitudes. Okay. 2. The top of Mount Everest, excuse me, is 8,850 meters above sea level. Using the graph, estimate the atmospheric pressure at the top of Mount Everest. Okay. So let me see. So that's 8,000. Every little box there corresponds to, let me think, 200 meters, right? Because it's 1,000 over 5. So yeah, 200. So 200, 400, 600, 800. So, and a little bit more. So somewhere there. So that point over there corresponds to about, okay, every box in the horizontal. So in the vertical direction, every little tick is 200. So 200 is the little box there. And in the horizontal direction, the x direction, every little box corresponds to 2 kilopascals. So we are in between. I mean, if you see, we are in between the first and second square. So that's about 31. Okay. So it's this value there, 31 kilopascals. And I was recently watching a documentary or a video, I don't know how you would call it, about how Everest is everything wrong with our world right now, because it used to be an adventure. I mean, adventurers and mountaineers used to climb Mount Everest, but now everybody and his mother tries to do that, and it became a tourist destination. And people die en route to that. They do TikToks and stuff like that. It's crazy. I actually didn't know about that. So yeah, speaking about Mount Everest. So let's move on to part 3. On a different day, the pressure at sea level is 104 kilopascals, and the pressure at the height of 2,500 meters is 74 kilopascals. Calculate the percentage change in pressure from sea level to the height of 2,500 meters. Incidentally, I'm from Cyprus. The highest mountain is about 2,000 meters tall. So yeah, I mean that would be the percentage change. I never thought about it. So let's do that. So So the percentage change should be, so let's write it like that. So we have 74 at the 2500 meters minus 104 kilopascals at sea level over the original, right? So 104 kilopascals at sea level, so kilopascals cancel, times 100. Okay, so this percentage is minus 30 over 104 times 100, which is, let me see, 30 over 104 times 100, so minus 28.8%, which is about minus 29%. Actually, it's significant. I didn't expect that. Okay. All right. D. Figure 12 is a model representing molecules of the Earth's atmosphere. So we have the top of the atmosphere, very few molecules, as you can see, and the molecules get denser as we approach the sea level. Okay. So use figure 12 to explain how the density of the air varies with height above sea level. So fig 12, okay, shows the molecules are densely packed at sea level, okay, and widely spaced at the top of the atmosphere, so near the top of the atmosphere. Okay, so since density is mass per volume, okay, the same volume at sea level contains more molecules than the top, right? Okay, so density decreases, okay, as height increases, okay. And we know this, those of you who travel, and let me know where you travel and if you travel in the comment section. And also, guys, please subscribe. 90% of the people who watches my videos are not subscribers, which is sad. So, I mean, you know that they need to pressurize the chamber when you fly above, I think, above 10,000 feet, you need to pressurize it, okay? Because the density drops significantly. And also, again, speaking about Mount Everest, I think at about 7 kilometers above sea level, maybe it's less. It's not something I will do or think about, but somewhere there you need oxygen. You know, uh, you need oxygen, otherwise you will die. You cannot breathe. Okay, it's too the density is too, the air is not thick enough. I mean, you don't get enough oxygen, you might die. So you need oxygen bottles. Okay, so let's move on to the next question. Okay, this has been an interesting test. I mean, it contains things that I don't know, I don't think about too often, if that makes sense. So let's move on. Okay, question 5. Figure 13 represents the Earth. Figure 13 shows two magnetic compass needles placed near to the Earth's surface, at points Q and T. Each magnetic compass needle can rotate about its central dot. Okay. Question I. A compass needle is placed at point P and another at point R near to the Earth's surface. On figure 13, draw an arrow at point P and an arrow at point R to show the direction of the compass needle at each point. So you can think about this as the compass needle points where the magnetic field points out of the page. Okay, so that's the magnetic north pole. Okay, and that's the magnetic south pole. So what I'm trying to say is that because at T the needle is perpendicular to the Earth's surface, that's the magnetic north. Okay, so the magnetic field goes into R pretty much. So at R, the compass will also point down, okay, because it points in the direction of the magnetic field, and the direction there is into the page. So it should be down, which is a little bit counterintuitive. We can draw more lines. So that's another magnetic field line, I guess. Okay. And the other thing that is kind of shocking with these things is that at P, you can, I mean, the magnetic field points in this direction up, so it's going to be parallel like that. Okay, I hope this makes sense. But compasses used to and often still confuse me. So, but the answer is this. Okay, so I hope it makes sense. If it doesn't, ask me in the comments, and I will provide better explanations. Question 2. Explain why the arrows point in the directions you have drawn in part 1. You may draw on figure 13 to help your answer. Okay, I mean, we just explained it. So we can write that the Earth creates its own magnetic field, its own, let's name it B for magnetic field. A compass needle aligns itself with the direction of B at the point. Okay, so at P, which is the equatorial region, okay, B is parallel to the surface. So at P, compass points up. Okay, and again, B is the magnetic field. Okay. What else? At R, near the geographic North Pole, okay, but magnetic South, okay, which is counterintuitive. We can write that B lines bend inwards, okay, so compass points down, okay, and what else? I mean, this is all you have to explain, right? And we can also, let me create a clean page. So at T, the field lines emerge from the Earth. Okay, which is consistent with the arrow shown. Okay, let's move on. Part B, figure 13 shows a wire placed between the poles of a U-shaped magnet. The wire is connected to a resistor and a battery. The wire carries a current in the direction shown. Okay. The wire is perpendicular to the magnetic field of the magnet. Draw an arrow on figure 14 to show the direction of the force F acting on the wire. Label this arrow F. Okay, we need Fleming's left hand rule. So Our index points in the direction of B. Okay, our middle finger is the direction of the current. Okay, and the thumb is gonna tell you the force. So let's go apply that. So B goes from the North Pole to the South. Let me use different colors. So let's use red. So the B points in that direction. Okay, so that's your B. Okay, and this is the direction of our index finger of the left hand. Don't forget that. Okay, and then we see that the current is indeed perpendicular to this B. Okay, so we put our middle finger in the direction of B, and our thumb points up, so the force is up. Okay, oops, let me use a different color. Let's use purple. Okay, so that's the direction of the force, and it's perpendicular to the wire. Okay, yeah, that's it. There is nothing more to add to question I. Okay, part 2, state 1, practical way of reversing the direction of the force. You can reverse the battery. Okay, so you can make this the plus and make this the minus. Okay, so reverse the direction of the current. So let's write that down. So swap the battery connections. Swap the battery connections. Okay, to reverse the current. Okay, and then you will have force downward. You can also turn the magnet around, I guess, to exchange. So you can rotate the magnet as well. So the south pole comes here and the north there. So that's another way to do it. But okay, they ask for one. So actually, let me write it down just so you have complete notes. So turn the magnet around. So north and south are exchanged. Okay, so that's the answer, and there is a third question. In figure 14, the current in the wire is 3.2 amps. The length of the wire in the magnetic field is 0.042 meters, and the magnitude of the force on the wire is 0.078 newtons. Calculate the magnitude of the magnetic flux density between the poles of the magnet. So we're going to use F Bill. I don't know if they teach it to you that way. So F is equal to the magnetic field, the magnetic flux density times the current times the length. So we need B, so we are going to be solving for B. So F over IL. So the force, our force is 0.078 newtons. The current is 3.2 amps, and the length is 0.042 meters. So this yields, it's a very weak magnet, by the way, 0.58 Teslas. Not very weak, okay. I underestimated it. It's good, actually, it's strong. Okay, so this was question 5. Let's move on to question 6. Which, okay, question 6. Which of these is a unit for the moment of a force? Okay, so the moment is force times distance, I guess. Okay, so the units will be newtons times meters. So C. Okay, B. Figure 15 shows a claw hammer about to remove a nail from a piece of wood. State the principle of moments. How is this related to the figure? Okay, I guess this is part 1 of question B. Okay, so it's not related. So the principle states that for a system in equilibrium, okay, the sum of all clockwise moments okay about any pivot point okay equals the sum of all anti-clockwise moments about the same pivot. Okay, moving on. Part 2, calculate the force F2 shown in figure 15. So they give us F1, D1, and D2, and we need to find F2. F2 is the force from the nail. Okay, so just F1 times D1 is equal to F2. I don't like using the cross. So F1 times, oops, what am I doing? Again, F1 times D1 is F2 times D2. So F2 is F1 D1 over D2, right? Did I mess up something? No. So F1 is 11.4 newtons times D1, 24.5 centimeters over 3.7 centimeters. Okay, so this is equal to 11.4 times 24.5 over 3.7. So 75.5. 75 point. It's 49, so I'm gonna write it 75.5 newtons. Okay, question C. Figure 16 shows a system of gears that are used in a clock. Okay, gear wheel P rotates clockwise at the rate of 1 revolution per minute. Calculate the rotation rate of gear wheel Q in revolutions per hour. So, okay, so 1 revolution per minute, 1 revolution per minute is going to be 60 revolutions per hour, pretty much, right? Because in 1 minute we have 1 revolution, so in an hour we have 60. So we can write it as 1 rev, and then we can write the denominator as or we can actually write, so I think I confused you already. So this is equal to 1 rev per minute times 60 minutes per hour. Okay, so we get 60 revolutions per hour. Okay, now the small gear, it has 20 teeth, so it will spin 3 times faster. Okay, because 60 over 20 is 3, or in other words, in 1 revolution of the big wheel, the small wheel will revolve 3 times, right? Because the ratio is 3. So the rotation rate of Q is 3 times 60, so 180 revolutions per hour. Okay, I hope this makes sense. I did a little bit on the fly, so I hope it makes sense. So let's move on. Part 2. Describe how a gear wheel could be added to the system to give a clockwise rotation with double the rotation rate of gear wheel Q. Okay, so we'll have to add another one. Your answer should refer to the position of the gear wheel and the number of teeth in the gear wheel. So, so Q rotates anti-clockwise. Okay. So we need a gear that rotates clockwise at double Q's rate. Okay. You don't need to write these, by the way. I just wrote them. I don't know why. So these are not the statements you need. So I'm going to put them in parentheses. So I'm just restating the problem pretty much. So we can write that a gear meshed with Q, okay, will rotate clockwise, okay, to spin at twice Q's rate, okay. It needs half of Q's number of teeth. So 10 teeth. Okay. So that's the answer, right? Yeah, I think that's good. So yeah, this was question 6. So let's move on to question 7. Okay, figure 17 shows an athlete training with a push sled. I've never seen something like this before. I guess you develop strength that way. Okay, so the athlete pushes the sled with a force of 645 newtons. Calculate the distance the sled moves when the force of 645 newtons does 7,440 joules of work on the sled. Give your answer to an appropriate number of significant figures. So, what do we need again? The distance. So the work done is force times distance. So distance is work over force, and the work is the energy by the athlete over the force. So 7,440 joules over 645 newtons. This yields how much? 11.53 meters, which is about, let's say, 11.5 meters. That's a good answer. Okay. How do I know that joules over newtons are meters? So joules are equal to kilograms times meters over seconds squared. And if I divide by newtons, newtons are kilograms times meters over seconds squared. So kilograms cancel, seconds cancel, and we are left with meters. Okay, let's move on. B. Figure 18 shows an electric motor lifting a set of masses. So, okay, we have the motor, the string, and the masses. Question I. Describe an experiment using the apparatus in figure 18 to determine the gravitational potential energy gained by the masses as they are lifted. Your description should include any measuring devices to be used. You may add to the diagram in figure 18 if it helps your answer. So we need use a balance to measure total mass in kilograms. Okay. Use a meter ruler, sorry, clamped vertically Okay, to measure the height, the masses are lifted. Okay, to measure the height, the masses are lifted. Okay, record the starting position of the mass, the starting and final position of the masses. Okay, using a reference point, I guess. Okay, measure the vertical difference delta H between the positions. Okay, and after you measure everything, GP is mass times G times delta H. G is 10 newtons per kilogram. Okay, moving on. Part 2. In one experiment, the change in gravitational potential energy of the masses was 5.8 joules. The total mass lifted was 320 grams. Calculate the vertical height the masses traveled through. And the height is in meters, whereas the mass is in grams. So don't get fooled by that. You need to convert to kilograms. Okay, so GP is mass times G times delta H. So delta H is what we are after. Is going to be equal to GP over mass times G. Okay, so 5.8 joules over the mass, 0.32 kilograms, and G is 10 newtons per kilogram. Okay, and joules over newtons yield meters, right? I'm going to examine that in a moment. So let me do the calculation first. So 5.8 over 0.32 times 10, 1.81 meters. Let's write 1.8 is good. So joules again is kilograms, meter squared over second squared, and then newtons is kilograms times meters over second squared. So everything cancels except the meters in the numerator. Okay, I don't know if they need you to know this, how to analyze units to their base quantities, but okay, maybe it's an overkill. Ignore it if you don't need it. And for those of you who are going to go on to study at the AS level and A level, and of course, university level physics, you need to know these things. So, okay. Part 3, the efficiency of the motor was 59%. State one reason why the motor was not efficient by 100%. Okay. So, friction in the motor, okay, causes heating. Okay, that's one reason. So some of the electrical energy, okay, is transferred to thermal store rather than going into lift. Question 8. A student investigates how current varies with potential difference across a filament lamp. The student uses a power supply, a variable resistor, the filament lamp, and 2 meters. Part of the circuit diagram is shown in figure 19. Complete the circuit diagram needed for this investigation. Okay, so I assume that's the lamp. Okay, so we need a voltmeter, an ammeter, and a variable resistor. So we can put the variable resistor here in series with the lamp. Okay, we can connect an ammeter to measure the current and a voltmeter here across the lamp to measure the voltage. So that's the voltmeter. Okay, so this looks okay. This awards 3 marks. Okay, that's a lot, I think. Let's move on. B. Another student repeats the investigation in part A using a data logger. Okay, the data logger, so this is a richer student that has access to equipment. Okay, you see how life can be unfair, guys. I'm joking, by the way. Okay, so let's continue. The data logger records observations using sensors instead of meters. The sensors are connected to a computer to collect and display the observations. The data logger collects 555 pairs of data in 2 minutes. Okay, the results are shown in figure 20. Okay, suggest one advantage of using a data logger instead of meters in this investigation. So, I mean, 555 pairs of data. Okay, so that's a good reason to write here. So, data logger collects 555 pairs of data in 2 minutes, far more than the student with the meters. Okay, so it collects data faster and it collects more data. Okay, part 2, describe how current varies with potential difference in the graph in figure 2. So we can see that as current increases, the potential difference also increases, right? But this is not a linear relationship. I mean, it's not a straight line like that. Okay, so we are going to describe this right now. So the relationship the relationship is non-linear. Okay, the graph is a curve, not a straight line. Okay, the rate, you can write that, the rate of current increase decreases, I'm gonna need an extra page, decreases at higher voltages. Okay, so what I mean is that here you see that the current increases steeply. I mean, if you think about the gradient, and then the gradient decreases and then decreases some more and keeps decreasing as the voltage increases. Okay, so it's not a linear relationship. Okay, part 3. Use data from the graph in figure 20 to show how the resistance changes with potential difference for a filament lamp. So how many points again? They don't specify points, so you can choose a few. Okay, so first of all, resistance is voltage over current. So let's go take some pairs of values. Okay, find the most convenient. That's what I try to do with these papers. So, okay, this point is kind of convenient. and then this point is kind of convenient. So here we have half a volt corresponding to 300 milliamps, and here we have 3 volts at how much is that? About 800 milliamps. Can we do one more? Let's do this point over there. So there we have 2.5 volts, and okay, every little deviation here is 20, right? So 720, 740, 760, 780. So we see that we have 740 milliamps. So let's name this 1, 2, and 3. Okay, so for 1, we have that the resistance is half a volt over 300 milliamps. Let's name it 0.3 amps. So the resistance there is 1.7 ohms. Then at point 2 we have the resistance of, so 2.5 over 0.74, so 2.5 over 0.74, so 2.5 over 0.74, we get 3.4 ohms. And then at point 3 we have that the resistance is 3 volts over 0.8, so 3 over 0.8, this yields 3.75 ohms. Okay, so we see that R increases as voltage increases and current increases. Okay, so is there anything else here? The reason, okay, so R increases because filament heats up. Okay, so yeah, that's the reason. Okay, part C, which of these equations is correct? So time is charge over current. This is confusing. So okay, current is charge per time. So charge per time. So time is charge per current. So that's option. Okay, option A, right? Yes. Okay, for a moment I was confused. I'm sorry. Okay, A is correct. So let's move on. Part D, the unit of work is the joule. Starting with the meaning of work, we may obtain an equivalent unit of work as newtons times meter. Using work equals to force times distance. Unit of work is unit of force times unit of distance equals to newtons times meters. The unit of potential difference is the volt. Explain how, starting with the meaning of potential difference, we may obtain an equivalent unit of potential difference. Okay, so potential difference is defined as energy transferred per unit charge. Okay, that passes between 2 points. Okay, so let me turn the clean page. So PD is energy per charge. Okay, which is equal to joules per coulomb. Okay, so since 1 joule is 1 newton times a meter, then the potential difference unit can be written as newtons times meters over coulomb. Okay, so that's the unit they are asking for. Okay, I don't think I ever encountered this before in my life. I mean, the volt expressed that way, but it's legit. So let's move on. Question 9. Which of these changes of state describes sublimation? Okay, so it's when we go from solid to gas, right? So C is sublimation, from solid directly to gas. It happens to ice, right? Yes. So part B. Figure 21 shows a sealed aerosol can. The sealed can is taken from a cold room into a warm room. If the volume of the can remains the same, which of these does not change? So the pressure inside the can increases because the temperature increases, and that makes the molecules move faster, more collisions, so more pressure. So it does change, so that's not the answer. B, the mean speed of the particles inside the can, that it changes. I mean, the speed changes because moving to a warmer room warms the gas, so the molecules, the particles move faster. C, the mean distance between the particles inside the can. Okay, that's a candidate because the volume is fixed and the number of particles is fixed. So yeah, that sounds plausible. Let's read D. D states the mean size of the momentum of the particles inside the can. That's gonna change, right? Because the energy increases, so momentum increases. So C is the correct answer. Okay, and the justification is that we have same V and same number of particles, so the average distance between them is going to be about the same. Okay, let's move on. Part C. Figure 22 shows a storage heater. The storage heater contains bricks. The bricks are heated electrically. The electrical heater supplies 210 kilojoules of energy to each brick in the storage heater. One brick has a mass of 5.8 kilograms. The specific heat capacity of the brick is 860 joules per kilogram per Kelvin. Use this data to calculate the increase in temperature of the brick. So delta Q is going to be C times M times delta theta. So delta theta is going to be delta Q over C times M. Okay, so we have 210,000 joules. Okay, then over the mass, which is 5.8 kilograms, and then we have 860 joules per kilogram per Kelvin. So joules and kilograms cancel, and the answer is okay. I have my calculator next to me to do this. So 42.1 Kelvin, so 42 degrees Celsius. So 42 is the meaning of life, guys, according to the Hitchhiker's Way to the Universe. So it's a silly reference to a book about space and exploration and stuff like that. Okay, part 2. The actual temperature increase will be smaller than what you calculated in 1. Explain why the actual temperature increase will be smaller than the value in 1. So the calculation assumes that all 210 kilojoules go into the brick, which is not the case. We will lose some heat to the surroundings. So some energy will be lost to surroundings. Okay, the air around the brick. Okay. So yeah, that's enough. So the brick receives less than 210 kilojoules. Okay, so that's the answer. Let's move on to part D. I haven't seen this asterisk in GCs yet, in the international GCSEs at least. So this is a long writing problem, which is my favorite, not my favorite. But okay, let's read it and actually do it. Okay. Okay, let's see. Describe an investigation to determine the value of for the specific heat capacity of water. Your answer should include details of the apparatus needed, the experimental procedure, and how the value may be calculated from the measurements taken. You may also draw a diagram to help your answer. So let's start with apparatus needed. So you will need an insulated container, okay, electric immersion heater to supply energy to the water, thermometer to measure the temperature, balance to measure the water's mass, I guess. What else will we need? Stopwatch to time the heating period. Okay, an ammeter and voltmeter. Okay, to measure the electrical energy supplied. The electric energy supplied. Okay, and a stirrer to ensure water heats evenly. Okay, so that's the apparatus though. So for the procedure, so measure M, record the initial temperature, immerse the heater, okay, switch on and start the timer, okay, stir water as it heats, okay, record, record I and V, and after time T, measure theta final, and to calculate C, you need delta Q. The input is going to be current times voltage times the time, okay? Delta theta is theta final minus theta initial. So C is going to be delta Q over mass times delta theta, and this will give you the specific heat capacity of water. Okay, let me just use a dot for the multiplication. I don't really like using cross. I guess it's a GCSE thing, but I don't like it. Okay, so this was question 9, and we are left with question 10. Okay, question 10, part A. Figure 23 shows a magnet being dropped through a coil. Oh, that's interesting. Okay. The coil is connected to a sensitive voltmeter. Okay, and there's a bubble wrap. Explain why the voltmeter shows a reading as the magnet passes through the coil. So let's write down that as the magnet falls through the coil, okay, its magnetic field lines cut through the turns of the coil. Okay, the magnetic flux through the coil changes. So the magnetic flux through the coil changes as the magnet moves. Okay, let's use a clean page. By Faraday's law, of electromagnetic induction, okay, a changing magnetic flux through a conductor induces a voltage across it. So a changing magnetic flux through a conductor, through a coil, okay, induces a voltage across it. Okay, so the voltmeter measures that induced voltage, which is the electromotive force, EMF force. So, okay, so let's move on to part 2. Another writing problem. Okay, so this is a tedious test. Okay, a student develops this investigation to find out how the reading on the voltmeter depends on the height the magnet is dropped from. Describe how the student could use the arrangement in figure 23 to do this investigation. So you can, he or she, I don't know, they can clamp a ruler vertically alongside the tube. Okay, hold the magnet at the chosen height above the top of the coil. Then release it. And let it fall. Okay. Record the maximum voltmeter reading. As the magnet passes through. Okay. Repeat the drop. From the same height several times. Oops. H means height, okay. From the same height several times, okay. And average. Okay, take the average. So increase the height in regular steps. So 5 or 10 centimeters maybe. Okay, and repeat the process. Repeat the process at each height. Okay. Keep the coil position at the same and the same magnet fixed through to make it a fair test. So keep the coil position the same, I guess. So don't change it. And plot a graph of peak voltmeter reading against drop height. Okay, so this is an okay answer, I hope. So let's move on. Part B, another long writing problem. Wow. Okay, so this is hard, guys. Okay, so okay, let's see. Is this the last one though? Yes. Okay. So a transformer converts a voltage of 11,000 volts to 230 volts. Explain how the design of this transformer enables the voltage to be converted from 11,000 volts to 230 volts. Your answer should include details of the structure of a transformer, how a transformer works using ideas of electromagnetic induction, excuse me, and how the design of this transformer enables this exact voltage of 230 volts to be obtained. You may draw a diagram to help your answer. So the 11,000 volts alternating supply drives, okay, so the 11,000 volts AC supply, okay, I'm gonna write it like that, drives a current through the primary coil. Okay, this AC current produces a continuously changing B and continuously changing magnetic field, right, in the iron core. Okay, the iron core carries this changing B to the secondary coil, this changing B to the secondary coil, and again B is the magnetic field, okay, so the secondary coil, okay. The changing B, so the changing, actually magnetic flux is proper, so the changing magnetic flux, okay, through the secondary coil, okay, induces an AC voltage in the coil by induction. Okay, so now how do we produce 230 volts? Okay, so the turns ratio equation is the voltage in the primary over the voltage in the secondary coil is equal to the number of turns in the primary coil over the number of turns in the secondary coil. Okay, so we see that we have 11,000 volts over 230 being equal to the number of turns in the primary over the number of turns in the secondary. Incidentally, by the way, here in Cyprus, you also have 230 volts because we used to be a British colony, I guess. Okay, so the number of turns in the primary is about equal to 48 times the number of turns in the secondary coil. Okay. So yeah, that's the answer. I mean, okay, I mean, if you want to draw a diagram, this is the iron core. Okay, something like that. So that's the iron core, and you have way more turns, so this is going to be your primary voltage. Okay, and you need lots of turns here. I don't know why it does that. Okay, so this is the primary, so NP, and then the secondary will be smaller, and you will get the secondary voltage there. Okay, so this was paper 2 from 2024. So this is the higher level test, and after finishing it, I see why it's the higher level test. It has a lot. It's a very dense paper, guys. So anyway, I hope this video is useful. I have to admit that I did this on a rush because I wanted to have a video out there for the viewers from England, because I do have Edexcel material for the GCSE level, which I started working on, but only for the international students. But I know that many viewers watch from England, so this is the first video at the GCSE level from England. Okay, I hope it's useful. I think the test is on Monday, so I'm gonna try to edit it fast and upload fast, so it is useful to you guys. So anyway, let me know what you think. Please like and subscribe. Now I set up a buy me a coffee link if you want to sponsor these videos. I mean, I make nothing from this so far, so, and I can't keep up with it forever for free, so I will need some, I don't know, so any help will do, I guess. So yeah, this is it. See you in the next